When considering the uncertainty in a value, we could assume that there is a number of small factors which are all having a random impact on the quantity that we are measuring. If you assume that there's an infinitely large number of uncorrelated factors which are all having an infinitely small impact on the variation of the measured quantity, then you can derive a theoretical equation for how the measurements should vary. The theoretical equation for the probability of attaining a value x is as follows. The equation is complicated, but you may recognize its shape. Sometimes it's called the bell curve. However, it's more formally known as the normal distribution or the Gaussian distribution. So in this case, the average value is represented by the Greek letter mu, and the Greek letter sigma represents what we call the standard deviation. And the standard deviation tells us how large the spread in the data is. So as we can see, the highest probability is that the measured value will be exactly the average value. However, there is still a significant probability that the measured value could be one standard deviation higher than the average value. However, the probability of being 3 standard deviations above the average value is almost insignificant. If we have a look here, the probability is very, very low. The normal distribution is symmetrical, and it lets us know that if we make a measurement, there is a 68.2% chance that it will be within 1 standard deviation of the mean. So that is between here and here. So that's pretty much a 2/3 chance that we'll be within 1 standard deviation of the mean. There's a 95.4% chance that it will be within 2 standard deviations of the mean. There's only a 0.3% chance that if we measured a value that it would be 3 standard deviations outside the mean. Now at this point, I just want to throw you a warning. Often in physics, we'll assume that there's a normal distribution, where this is in fact not true. We often make some assumptions that aren't entirely true in physics. You would only expect to see a Gaussian distribution if there's a large number of small, uncorrelated factors that are contributing to the outcome of a measurement. Often, however, there is a correlation between the factors, or some of the factors may be large in their impact. This means that there is a tendency for rare extreme events to occur more often than predicted by the normal distribution. This may be a contributing factor to why climate change modelling does not accurately predict how often we get extreme, 1 in a century, floods, fires, or droughts. Simply assuming that you have a certain distribution is dangerous in the real world and has led to a number of problems in history. For example, the financial modelling that took place before the global financial crisis. And some scientists have falsely claimed that they measured temperatures colder than absolute zero by not doing their statistics correctly. So it's easy to assume that you have a normal distribution. However, if you are doing calculations which have consequences in the real world, it is important to check these assumptions.